to today's lecture on fundamentals of electrical drives. Myself, Dr. Shimpi Ralhan, Professor, Sri Shankaracharya Technical Campus. In the previous lectures, we have already discussed the basic fundamentals of AC and DC machines. In today's lecture, we will explore the basics of drives, covering the components of electrical drives, selection factors for different applications, types of drives, types of load torques, heating and cooling of a motor under different loading conditions, and the standard ratings for motors. The basic block diagram of the electric drive is shown in the figure. The entire unit consists of an electric motor, the energy transmitting shaft, and the control equipment, which is known as the electrical drive. The drive system can be defined as the combination of an electrical drive and the corresponding load. Basically, the control equipment consists of various contactors, relays, switches, potentiometers, and number of electronic devices like diodes, transistors, and thyristors. By using a control equipment, the efficiency of electric motor over a wide range of speed can be improved. The electric motors are the most commonly used prime movers in industrial equipment, as their characteristics can be adjustable over a wide range, such as speed torque and speed current, which can be controlled with suitable equipment. They offer the advantage of changing operating conditions according to the load demand and can integrate the protection circuits as well. With a high starting torque, the electric motors can start under load and achieve precise speed control with an accuracy of up to 1%. Additionally, they are easy to maintain, making them an ideal choice for industrial applications. So, if we see the components of the electrical drives, you can see from the block diagram that it consists of power source, power processor, motor, load, and a control unit along with the feedback systems. So, the systems which are employed for the motion control, they are called as drives, and the prime movers such as diesel or petrol engines, gas or steam turbines, hydraulic motors and electric motors for supplying mechanical energy can be used. For motion control, drives which employed with electric motors are known as electrical drives. The main components, as we have discussed, are motors, power processor, control unit, and electrical source. The load is usually mechanically designed to achieve a given task, for example, fans, pumps, robots, washing machines, machine tools, trains, drills, etc. The load requirement can be specified in terms of speed and torque demand. A motor having speed torque characteristics and capabilities compatible to the load requirements is chosen. So, let us discuss the components one by one in details. Motors act as energy converters by converting electrical power into mechanical energy. In braking mode, the power flow reverses. This allows energy to be fed back to the source instead of being dissipated as heat. Now, depending upon the type of power converter, there are several types of motors which are used in electric drives, and their choice depend on the type of demands on applications, cost, environmental factors, and also type of sources available. Broadly, they can be classified as either AC or DC motors. The DC motors, which can be wound or permanent magnet, AC motors like induction motors, squirrel cage or wound rotor, synchronous motors, wound field or permanent magnet, brushless DC motors which require power electronic converters, stepper motors, synchronous reluctance motors or switch reluctance motors. Next is the power processor or power modulator. Since the electrical sources are normally uncontrollable, it is therefore necessary to be able to control the flow of power to the motor. This is achieved by using power processor or power modulator. With controllable sources, the motor can be reversed, can be stopped, or can be operated with variable speed. Modern electric drives normally use power electronic converters to shape the desired voltage or current supplied to the motor. The power electronic converters have several advantages over classical methods of power conversion, such as they are more efficient since ideally no losses occur in power electronic converters. They are flexible. Voltage and current can be shaped by simply controlling and switching functions of the power converters. They are compact, smaller, and higher rating solid state power electronic devices are continuously being developed. The power modulators or processors are divided into three groups, namely converters, variable impedance, and switching circuits. Converter is used to convert and possibly regulate, that is using closed loop control, the available sources to suit the load, that is motors. These converters are efficient because the switches operate in their either cutoff or saturation modes. So, we have a combination of several conversions. Let us see one by one what are they. The AC to DC converters. This converter is used to get DC supply of fixed voltage from the AC supply of fixed voltage. AC voltage controller or AC regulator. These are employed to get variable AC voltage of the same frequency from a source of fixed AC voltage. Choppers or DC to DC converters are used to get variable voltage DC from a fixed voltage DC and are designed using semiconductor devices such as power transistors, IGBTs, GTOs, MOSFETs, etc. Output voltage can be varied steplessly by controlling the duty ratio of the device by low power signals from a control signal. Then we have inverters which are employed to get a variable frequency AC supply from a DC supply. The cycloconverters convert fixed AC voltage and frequency to variable AC voltage and variable frequency. The second class is the variable impedances. The variable resistors are commonly used for control of low cost DC and AC drives and are also needed for the dynamic braking of the drives. Variable resistors may have two or more steps and can be controlled manually or automatically with the help of contactors. The stepless variation of resistance can be obtained by using a semiconductor switch in parallel with the fixed resistance, and the variation of duty ratio of the switch gives a stepless variation in effective value of resistance. In high power applications, liquid rheostats known as slip regulators are employed to get the stepless variation of resistance. Inductors, usually in two steps, that is full and zero, are employed for limiting the starting current of the AC motors. Old drives may also employ saturable reactors for the control of induction motors. The third category is the switching circuits. Switching operation is required to achieve one of the following things, that is for changing the motor connection to change its quadrant of operation, for changing motor circuit parameters in discrete steps, for automatic starting and braking control, for operating motor and drives according to a predetermined sequence, to provide interlocking, to prevent maloperation, to disconnect the motor under abnormal or faulty conditions. So, the next component of the drive is control unit. The complexity of the control unit depends on the desired performance of the drive and the type of motors used. A controller can be a simple consisting of few op-amps or few digital ICs, or it can be as complex as the combination of several digital signal processors, DSPs. So, the type of main controllers can be as follows: analog, which are noisy and inflexible, but analog circuit ideally has infinite bandwidth. Digital, which are immune to noise and configurable. The bandwidth is obviously smaller than the analog controller and it depends on the sampling frequency. Then we have DSP or microprocessor controllers having flexible lower bandwidth compared to above. DSPs perform faster operation than microprocessors. With DSP or microprocessor, complex estimations and observers can be easily implemented. So, this is the advantage of DSP on both analog and digital. Electrical motors are generally reliable and they require minimal maintenance if chosen appropriately. Therefore, we must carefully consider their selection for different applications. Let us have a look at the factors which are usually considered before making the final decision on a motor. The first one is nature of electric supply, whether AC or pure DC or rectified AC supplies to be used for motor. The second is nature of the drive, whether the motor is to be driven as individual machine or group of machines. Then is the nature of load, whether the load requires light or heavy starting torque, load torque increases with speed or remains constant, whether the load has heavy inertia which may require long starting time. The last component is the electrical source. Electrical sources or power supplies provide the energy to the electrical motors. For high efficiency operation, the power obtained from the electrical sources need to be regulated using the power electronic converters. The power sources can be of AC or DC in nature and are normally uncontrollable, that is, their magnitudes or frequencies are fixed or depend on the sources of energy such as solar or wind. AC source can be either 3-phase or single phase. 3-phase sources are normally for higher power applications. Coming to the fourth point, the electrical characteristics of motors such as starting characteristic, running characteristic, speed control, braking characteristics are also considered for the selection of the motor. Also, the size and rating of the motor is important and has to be considered. That is, whether the motor is to run continuously, intermittently or on a variable load cycle, whether the overload capacity and pull-out torque are sufficient. Then the mechanical considerations such as type of enclosures, type of bearings, transmission of drive, noise level are also crucial during selection. Lastly, after taking into account all the factors, the capital cost and running cost are also taken into consideration for the selection of the motor. Now let us see what are the different types of drives based on their operation. We have three groups, that is a group drive, individual drive and multi-motor drive. Group drive is a type of drive which consists of only one electric motor driving several machines. Such a system where many machines are driven on one shaft and driven by a single electric motor is termed as shaft drive also. Now, the various machines connected to the same shaft may require different speeds, so multi-step pulleys and belts are used here. Group drives have their own advantages and disadvantages. Let us have a look on it. If we talk of advantages of group drive, initial cost of the group drive is less as compared to that of the individual drive. And also if we see the sequence of operation, group drive is useful because all the operations are stopped simultaneously. Less space is required in group drive as compared to individual drive. Maintenance cost is also low and requires little maintenance as compared to individual drive. The group drive has certain disadvantages also. The power factor is low. If all the machines are not working together in group drive system, then the main motor shall work at very much reduced load. This leads to reduced efficiency. Also, in group drive, if the main motor fails, the whole industry will come to a standstill. Hence, they are not very reliable. This arrangement is not suitable for the place where flexibility is the prime factor. They does not provide constant speed. Lastly, the group drive is not suitable for driving heavy machines such as cranes, lifts, hoists, etc. The second category is the individual drive, and in this type a single electric motor is used to drive one individual machine. That is why the name individual drive. Though it costs more than the group drive, but each operator has complete control on machine, which enables the operator to either increase the speed of motor or to stop it while not in operation. Also, the machines can be located at convenient places. If there is a fault in any one of the motor, this will not affect the production of the industry appreciably. Individual drive has many advantages when they are used. The individual drive gives desired operation as each machine is driven by its own individual motor and works at good power factor. Efficiency of the system is high. Individual drive is more reliable. We can fit the machine wherever convenient. It is more useful where constant speed is required and suitable for driving heavy machines such as lifts, hoists and cranes, which was a limitation in case of the group drives. The third one is the multi-motor drive. If in a system a separate motor is provided for driving the separate mechanism, the system is called multi-motor drive. Such a drive finds its application in travelling cranes, rolling mills, complicated tools, etc. Such a system facilitates automatic control for each operation, increasing the overall productivity, and it ensures optimum running conditions of various mechanisms. Multi-motor drives, where multiple motors are used in a single application or machine, offer several advantages that can be very important in industrial settings. Let us see some of them. Multi-motor drives increases the reliability of the system. Say if one motor fails, others can continue to operate, thereby reducing the downtime and preventing complete system shutdown. The first one is redundancy and reliability. Multi-motor drives increase the reliability of the system. Suppose if one motor fails, others can continue to operate, thereby reducing the downtime and preventing the complete system shutdown. This redundancy is crucial in critical applications where continuous operation is essential. Next is the flexibility and control. Using multiple motors allows for more precise control over machine functions. Each motor can be controlled independently, which enhances the ability to fine tune the processes and improve the quality of the output. This is particularly very important in complex machinery which is used in manufacturing, packaging and printing industries. Then comes the load sharing. Multi-motor drives distribute the load among several motors, which can reduce the stress on individual motors, thereby extending their life and reducing maintenance requirements. This load sharing also allows for use of smaller motors, which can be more cost effective and energy efficient. Next is the increased efficiency. By optimizing the load on each motor, the drives can operate more efficiently and each motor can run at optimal speed and torque, maximizing efficiency and minimizing the energy consumption. Also, the multimeter systems can improve the dynamic response of a machine. For example, in a conveyor system or large milling machine, having multiple motors can help achieve more uniform speed and torque distribution along the process line, leading to smoother operation. Again, the multi-motor drives are very much cost effective regarding their maintenance and replacement. The maintenance can be more manageable and less costly, as the motors can be serviced or replaced individually without shutting down the entire system. So, this helps in reducing the operational interruptions and maintenance costs. Different motors can be specialized for various functions within the same system. So each motor can operate under conditions that best suits its design characteristics. So this specialized motor use can lead to better performance and long life of motors. Now after discussion till now, let us see that what are the factors which affect the selection of electric drive. The selection of electric drive basically means the selection of drive motor. So it is very important that how we are going to select our drive motor. The various factors which affect the selection of motor to drive the load are enumerated here. Let us have a look on them. The range over which the speed control is necessary for the load. Similarly, how hard is to control the speed, and the speed regulation affects the choice of the motor. The motor efficiency varies as load varies. So, efficiency consideration under variable speed operation affects the choice of the motor. The braking requirements from load point of view, easy and effective braking are the requirements of a good drive. The starting torque is necessary for the load. The corresponding starting current drawn by the motor affects the selection of the drive. It is well known that running of motors with low power factor values is not at all economical, and the power factor varies with the load conditions in some motors. Hence, the type of load and the running power factor of the motor are the essential considerations while selecting a drive. There are variety of types of load conditions possible like continuous, intermittent, impact, etc. and such load variation factor and duty cycle of motor influences the selection of drive. The motors available are AC or DC, but the availability of supply decides the type of motor to be selected for the drive. There is possibility of frequency supply variations, and the motor selected must be able to withstand such supply variations. The size and rating of the motor decides its initial cost, while the various losses, temperature rise decides its running cost. So, the economical aspects must be considered while selecting a drive. It is also important to study the conditions of stable operation of an electric drive, which includes the investigation of reliability of operation. So, reliability is an important consideration for the selection. It is possible that the atmosphere where an electric drive is to be used may contain some chemical gases, fumes, may be humid, etc. So, such contaminated atmosphere or humid atmosphere affects the choice of motor for a drive. So, studying of all these factors leads us to proper selection of an electric drive and a proper drive system for the load to be driven. Not only the selection, but it may be possible to modify the system performance and make it more economical and efficient, which already exists. Load torque is a critical factor in the operation and the performance of drive systems. Load torque is essential for the motor sizing and selection, energy efficiency, control and stability. So, let us study that what this load torque is. The load torque has the potential to drive under all conditions, and it always opposes the motion, and its sign changes on reversal of motion. There are two types of loads, those which provide active torques and those which provide passive torques. Active torques arises from gravitational forces, as we can see in hoists, lifts and railway locomotives on slopes, or from elastic deformation such as during the compression or release of springs. So, active torques are linked to changes in potential energy. For instance, during the upward movement of a load or compression of a spring, the potential energy increases and the torque opposes this action. Conversely, during the downward movement or spring release, the potential energy decreases and the torque facilitates the action, maintaining its direction even if the drive's direction reverses. Passive torques whereas arises due to friction or due to shear and deformation in inelastic bodies such as lathes, pumps, fans, etc. They always oppose the motion, retarding the rotation of the driven machine. Moreover, with change in direction of motion, the sense of torque also changes. For example, when a weight is raised upward, the friction torque adds to the useful torque, but when lowered down, it subtracts from the latter. After seeing the load torque, let us now see what are the various components of the load torque. They are friction torque, windage torque, and the torque required to do the useful mechanical work. Friction torque occurs at the motor shaft and various parts of the load, with its equivalent values referred to the motor shaft. It varies with speed, as you can see in the figure A, where it is much higher at standstill than just above the zero speed. This high initial friction is known as stiction or static friction. To initiate the movement, motor torque must surpass this stiction. Friction torque comprises of three components, including viscous friction, which varies linearly with speed, given by the expression T is equal to B into omega, where B is the viscous friction coefficient. Another component Tc, which is independent of speed, is known as the Coulomb friction. The third component Ts accounts for additional torque present at standstill. Since Ts is present only at standstill, it is not taken into account in the dynamic analysis. The second component is the windage torque, that is when a motor runs, wind generates a torque opposing the motion. This is known as the windage torque Tw. Windage torque is proportional to the square of the speed, given as T is equal to C into omega square. The third component is the torque required to do the useful mechanical work. The nature of this torque depends on particular application. It may be constant and independent of speed. It may be some function of speed. It may depend on the position or path followed by the load. It may be time variant or it may be time invariant. Load torque can be classified into torque varying with speed and with time. If we see the variation with speed, load torque can be classified as number 1, constant load torque. The torque is independent of the speed and is constant. At low speed hoist is an example of load where torque is constant and independent of speed. At low speeds, the windage torque is negligible. Therefore, net torque is mainly due to gravity, which is constant and independent of speed. We can say that paper mill drive is an example of it, and you can see the characteristics shown. The second one is load torque versus speed. The torque increases linearly with speed as shown, and this occurs in the case of fluid friction where lubricant is used. Then we have load torque versus the square of speed. The torque increases as a square of speed and occurs in case of air and fluid friction, such as in fans, compressors, aeroplanes, centrifugal pumps, ship propellers, high speed hoist, traction, etc. Then we have load torque, which varies as 1 by speed. This occurs where deformation of material takes place, for example in grinding and metal drawing. The second one is the variation of load torque with time. Depending upon the time for which the load exists on the electric drive, the load torques can be classified as continuous and constant load. For example, in centrifugal pumps operating under same condition for a long time. Continuous but variable loads, example hoisting winches, conveyors, etc. Short time intermittent loads, example excavators, cranes and hoists. Then we have pulsating loads such as in reciprocating pumps in textile looms. Then we have impact loads such as in rolling mills, forging hammers, shearing machines, etc. Such machines have flywheels attached with them for load equalization. Now, what is this load equalization? In many industrial drives such as in rolling mills, planing machines, electric hammers, presses, reciprocating pumps, the load fluctuates over a wide range in the space of few seconds. So, it is desirable to smoothen out the fluctuations in load, otherwise during the interval of peak load it will draw very heavy current from the supply, either producing large voltage drop in the distribution system requiring cables and wires of heavy section, and the process of smoothing out of the fluctuations in the load is known as load equalization. This is a very important process which has to be taken care of while driving the electric drives. In this process, energy is stored during the interval of flight load and is given out during the interval of peak load. Thus, the power drawn from the supply mains remains almost constant. The most common method of load equalization by use of flywheels. During the light load period, the flywheel accelerates and stores the excessive energy drawn from the supply, and during the peak load periods, the flywheel deaccelerates and supply some of its stored energy to the load in addition to the energy supplied from the supply. Thus, the load demand is reduced. We have already seen the factors which are affecting the selection of motor power rating. We have to also understand the heating and cooling of motor under different loading conditions for selection of motor power rating. So, it is definitely influencing the selection of motor power rating as the loading conditions keep on changing. So, let us see the heating under load. When a motor runs under load, it transforms some electrical energy into mechanical energy and the rest is usually released as heat. The motor's efficiency dictates how much energy is lost as heat. Its power rating should be sufficient to handle situations where motor is working at full load capacity and producing the most heat. The cooling capacity. The motor's ability to dissipate heat is equally important. The cooling system like fan or liquid cooling needs to be effective to stop the motor from overheating and getting damaged during constant use. Then the continuous operation near or at the motor's maximum power rating can lead to thermal overload if it is not properly cooled. This could cause motor failure due to insulation damage, bearing failure or other heat related issues. Therefore, the power rating should include a safety margin to handle occasional peaks in the load without overheating. Duty cycle is also very important to be considered, and it is a measure used to describe the operating pattern of a machine or device over a period of time. The duty cycle or the ratio of the time the motor spends running to the total time affects the choice of power rating. Say if a motor runs for 1 minute and rests for 3 minutes, the duty cycle would be 25%, meaning the motor is operating 25% of the time and resting 75% of the time. The motors are designed for intermittent duty and they can cool down during the off periods. So, a higher power rating is possible compared to a motor that operates continuously. Then the ambient temperature or the environmental conditions in which the motor operates also affects its power rating. Higher surrounding temperature makes it harder for a motor to cool down. This requires either a reduction in power usage or better cooling techniques to ensure that the motor keeps working reliably. So, the heating and cooling curves are to be studied for the implementation of the electric motors in the drive. If we consider a homogeneous machine developing a heat internally at a uniform rate, and this it dissipates to the surrounding and is proportional to temperature rise, it can be proved that the temperature rise of a body obeys exponential law. If we consider a homogeneous machine developing heat internally at a uniform rate and gives it to the surroundings proportional to the temperature rise, then we see that the temperature rise of the body obeys exponential law given by the expression where theta is rise in temperature above the ambient temperature in degree centigrade, and the final temperature rise with continuous load in degree centigrade is theta f. Here the heating time constant is denoted by tau given as Gs divided by A into lambda, and T is the time period. Here G represents the mass of the machine, S is the specific heat, A is the area of cooling surface, and lambda is the rate of heat dissipation. When the machine is switched off from the main supply or when the load on the motor is reduced, the machine cools. So, the curve that is plotted is known as a cooling curve. The expression for the cooling curve is shown, and it also shows that the cooling curve is exponential in nature. Let us see that what are the standard ratings for the motors. The rating of electrical machine indicates its load capacity limited by the considerations of temperature rise. According to ISI specifications, three kinds of ratings are generally specified. That is, the first one is a continuous rating. It is a maximum load which the motor is capable of delivering continuously for an indefinite period without the temperature exceeding the specified limits, and it is also capable of undertaking 25% overload for a period exceeding 2 hours under the same conditions. Thus, if motor is rated continuous 10 HP say, it means that it is capable of giving an output of 10 HP continuously for an indefinite period and 12.5 HP for a period of 2 hours without the temperature exceeding the specified limits. The second one is continuous maximum rating. The continuous maximum rating refers to highest power output that the motor can sustain indefinitely without exceeding the overload capacity. Here we cannot overload the machine. So, this is the output which the motor can give continuously for a long time without exceeding the temperature rise. The motor cannot give any overload and is used for motors of size larger than 25 HP per RPM. Third one is short time or intermittent rating. This is the output which a motor can deliver for a specified period, say 1 hour or 1.5 hour or 1/4 of hour, say, without exceeding the specified temperature rise. Unlike the continuous maximum rating, which is meant for indefinite operation under constant conditions, the short time rating is designed for scenarios where the motor operates at a higher load than usual but only for a limited duration, typically ranging from a few minutes to a few hours. Short time rating indicates the maximum load of the motor for the specified time followed by a no load period during which the machine regains its original temperature and cools down. Intermittent rating of a machine is defined as that load which is applied during a certain fraction of time of a load cycle and the temperature rise limit is not exceeded. So, motors with short time or intermittent rating typically require cooling down periods after operating at a short time rating. These periods help to dissipate excess heat that is accumulated during the high load phase. So, till now we discussed the essential components of electrical drives including the motor, power controller and the control unit. We explored the criteria involved in selecting drives for specific applications, emphasizing the various factors like power requirements, speed control, environmental conditions and efficiency demands. Understanding different types of load torque such as constant and variable torque was also highlighted, illustrating how they influence the choice of the drive system. We also examined how motors manage heat, the impact of various loading conditions on motor temperature, and the importance of proper cooling systems to maintain motor efficiency and longevity. Finally, we covered the standard ratings for motor including continuous, intermittent and short time rating, which are crucial for selecting the right motor for specific operational demands. Thank you. Thank you very much.